Yo, in this video, you'll learn everything you need to know about H-bridge motor drivers, how they drive motors, how to use them with a microcontroller to control the speed and direction, and all the different kinds of motor drivers so you can figure out which one is right for you. Okay, what's a H-bridge? A H-bridge motor driver is an electronic circuit that allows you to accurately control a DC motor's speed and direction. When current flows through the motor, it generates a magnetic field, which creates a rotational force in the rotor. By the way, the rotor is the name of the part that spins. The amount of voltage applied across the motor affects how much current flows through. The more current, the stronger the magnetic field is, which means the rotor spins at a higher velocity. And if you reverse the voltage, it'll spin in the opposite direction. So how does the H-bridge work? A H-bridge driver allows you to reverse the voltage across the motor using a clever configuration of switches. This is the circuit diagram of a H-bridge motor driver. It's got 4 switches and the motor is in the center. The diagram kinda looks like a H, which is why this circuit is called a H-bridge. I'm gonna build this circuit in real life to demonstrate the H-bridge. Pressing switches 1 and 4 will make the current flow from left to right, so the motor spins clockwise. Now this is what it's like in the real circuit. Pressing switches 2 and 3 will make the current flow from right to left. This current is now inverted, and so the motor will spin anti-clockwise. And of course it works in the real circuit. Make sure not to turn Q1 and Q2 on at the same time, because you'll get a short circuit. There's a bunch of current flowing through the switches and none through the motor. The same applies to Q3 and Q4. So that's the basic concept of the H-bridge. However, you don't want to be manually pressing and releasing buttons to control your motor. So we'll use transistors instead of push switches, so later we can connect a microcontroller and control this motor by writing some code. So let's connect 4 transistors on a breadboard. The type of transistor I'm using are MOSFETs, and I'll be using P-channel MOSFETs for Q1 and Q3, and N-channel MOSFETs for Q2 and Q4. The microcontroller I'm going to use to control this motor is the Arduino Nano. When I apply 5 volts to the gate of the N-channel MOSFET, it starts conducting, and with 0 volts, it stops conducting. The P-channel MOSFET works in the opposite way. So when I apply 0 volts, it starts conducting, and when I apply 5 volts, it stops conducting. But why use P-channels at all though? P-channel MOSFETs tend to be more expensive and more inefficient. Why can't you just slap on 4 N-channels and call it a day? The reason why P-channels are used up here instead of N-channels is because N-channels require the gate voltage to be at least 5 volts higher in order for it to conduct properly. Since the MOSFETs up here are connected to the high side of the circuit, the voltage at the MOSFET pins are already at 5 volts, so the gate voltage would have to be at least 10 volts so that it's 5 volts higher than this point of the circuit. With P-channel MOSFETs, instead of needing the gate voltage to be 5 volts higher, it needs to be 5 volts lower to conduct. Since the MOSFET is at 5 volts, simply connecting the gate to 0 volts will make it conduct. Providing a 0 volt signal is much easier than generating a 10 volt signal, which would require a separate circuit. This is why P-channel MOSFETs are commonly used on the high side of motor drivers. It's worth pointing out that the breadboard circuit I'm about to make isn't how H-bridge motor drivers are normally found in the wild. They'll typically be used in pre-made circuit boards or modules, or even ones that you design yourself. This motor driver that I made for another project uses the same working principles as the one I just explained, but it's in a nicely packaged PCB rather than a loose breadboard. So now is probably time to mention the sponsor of this video, JLC PCB, the one-stop manufacturing platform for everything PCB related. I designed this motor driver PCB in KiCad, then sent the Gerber straight to JLC. After a quick review and 24 hours for them to cook up my beautiful circuit board, it arrived at the crib shortly after. The whole process is really streamlined and cheap. Like it starts from $2 a board for prototyping and assembly, which honestly is a freaking steal. Gotta say I'm quite a fiend for their services. But yeah, hopefully you'll see this entire project and more PCB stuff in another video. If you want to know more about what JLC is capable of, check the link in the description. Now let's get back to making this breadboard H-bridge. In order to use the Arduino with the MOSFET, we'll need to connect a resistor in series with the gate to limit the current. And while we're at it, I'm just going to connect an LED in parallel to each of the gate pins so you can see clearly when the MOSFETs are on. Also, when working with components that generate magnetic fields like motors and other components that are sensitive to voltage spikes, it's important to use protection against inductive spikes generated by the motor. Inductive spikes happen when current suddenly stops flowing through the winding of the motor, which makes the magnetic field collapse and creates a large voltage spike. This voltage spike can easily fry sensitive components like MOSFETs. So 4 diodes are normally placed here. When Q1 and Q4 are on, current flows from the positive voltage through Q1, through the motor from left to right, through Q4 to ground. When Q1 and Q4 switch off, the motor's inductance tries to maintain the current in the same direction. D2 becomes forward biased as the voltage at its cathode drops below battery voltage. D3 becomes forward biased as the voltage at its anode rises above ground. Current now flows from ground, through D2, through the motor, still left to right, through D3 and back to battery voltage. This path allows the inductive energy to dissipate safely without causing a voltage spike. So that's for one case. When Q2 and Q3 are on, then switch off, the same thing happens but to the other side. Also, there's another clarification I should make because I see a lot of beginners getting confused. A H-bridge is not a half-bridge.
No.
It's easy to get them mixed up because they have similar names, but a H-bridge describes the full bridge, whilst a half-bridge is only one side of the full bridge. Cool, now you've got a really strong understanding of what a H-bridge motor driver is. Now here's how to use it with a microcontroller. I'm going to connect an Arduino Nano to the gates of all the transistors and write some code to turn Q1 and Q4 on, then turn it off, wait a bit, then turn Q2 and Q3 on, then turn it off, wait a bit, and repeat that over and over. Boom! Now let's control the speed. The speed of the motor is determined by the average voltage of the motor. So a higher voltage will result in a higher speed. To change the voltage, we use a method called pulse width modulation, or PWM for short. You want to pulse on and off really fast so that it averages out to a lower voltage. Let's take this LED for example. Now I'm going to apply a PWM signal. It looks like it's getting dimmer and dimmer. Now it's at 20% power of what it was before. Now let's slow-mo this footage. As you can see, the LED is actually just turning on and off really fast. It's on 20% of the time and off 80% of the time. This same concept can be applied to the motor. Here is the same signal but connected to the Q1 and Q4 gates, and as you can see, it's gradually slowing down. Now, by using the H-bridge and applying the signal to Q2 and Q3 gates, we can switch the direction and use PWM to gradually speed it up in the other direction. Now let's slow-mo this footage too because you can't really see the direction it's spinning in because it's so fast. As you can see, it spins one way, then slows to a stop, then slowly ramps up in the other direction. Let's freaking go! That's cool and all, but you would never use this H-bridge in an actual project. It's big, inefficient, and uses temporary connections. As mentioned earlier, this breadboard H-bridge simply makes it easier to understand the theory behind it. There exist motor driver ICs like this L293D, which has a breadboard compatible package, or this DRV8873, which is even smaller and requires you to surface mount solder it to a circuit board to use it. Basically, someone took this whole circuit and put it on a single chip. And because it's an integrated circuit with one purpose, it's generally cheaper, smaller, more efficient, and comes with extra features like overcurrent protection and thermal shutdown. I look through the catalog of these companies when I need to find a motor driver IC, TI, STM, or analog. Sometimes I'm not bothered to design a whole circuit just to use an IC, so I'd use a pre-made board. This one is a very popular motor driver, the L298D. It gets the job done and is really popular because it was one of the first mass-produced hobbyist H-bridge motor drivers. It's kind of like the Arduino of motor drivers. It's a great starting point, however it's big, bulky, and inefficient. This thing can only handle 4 amps max whilst needing this big ass heatsink. This motor driver IC can handle 10 amps and is tiny. Newer tech is nuts. Once again, I'll look through the catalog of these companies when I need a pre-made board. And that's all the source I have on H-bridge motor drivers. Appreciate you for watching and I'll see you soon.